A common task in reactor design is to determine the appropriate CSTR volume V that you need to obtain a target level of conversion. At steady state, no accumulation of species A. You have flow rate in of species A, FA naught. This is your flow rate out term, and this is the rate of generation of species A, which is usually going to have a negative sign right in here. Will have a negative value, I should say, not an explicit negative sign. Okay, if we go through and we just rewrite this, simplifying these first two terms, the usual thing that happens here is that you end up with 0 equals FA naught X plus RA times V. And now if I solve for V, I get that it's minus FA naught times X over RA. Now if you look at this, and I think of it first as the product of X across the bottom axis, and a height, FA naught over RA, RA being a function of X, determining the vertical axis, then I have my x-axis going this way from 0 to 1. This point x in here, this intermediate point, is my target conversion, and the height of this rectangle in here is FA naught over RA, where RA is evaluated at that point x on the curve. So if I now create a little box out of this, it gives me the volume that corresponds to the reactor that I need to reach that point x. So this is called a Levenspiel plot. It's for this particular Levenspiel plot is for a CSTR. Okay, what I'm going to do now is to extend this idea using these Levenspiel plots to work with reactors in series. So let's talk first about this case where we have two CSTRs in series. They're going to have volumes V1 and V2. And we're going to let x1 be the conversion that's achieved after we've come out of reactor 1. And then measured from a conversion of 0, we're going to let x2 be the conversion that's achieved after we've left reactor 2. So I want to emphasize that this is not the conversion of the amount of A that pours in to reactor 2. This is conversion measured from relative to this stream's composition, the one that was coming into the whole reactor assembly. That's an important point. Those are two very different things. Okay, so what we're going to do now is to show how you can determine the values of x1 and x2 from one of these Levenspiel plots. Okay, so we're just going to go through and do it twice. Then the first one has a species balance equation. You have 0, flow in, flow out. Notice it's at x1 for conversion level x1. And then we're evaluating the reaction rate, the generation rate, for the contents of reactor 1 being at condition x1, and multiplying by the volume of reactor 1. Now we can go through and build a similar equation for reactor 2. We have 0 on the left, flow into the second reactor, which is given by this. We have flow out of the second reactor, which is given by this. And then rate of generation in the second reactor is evaluated at conversion x2 multiplied by V2. Okay, now what I'm going to do is I'm going to rearrange these two equations so that I solve for V1 and V2 and try and write these in a suggestive form. So the first one, I rearrange it to minus x1 times FA naught over RA evaluated at x1. The second one, I'm going to write V2 is minus the difference between x2 and x1 multiplied by FA naught divided by RA naught evaluated at x2. Okay, so now if you, again, create a Levenspiel plot, we have our x-axis, our conversion axis across the bottom, going from 0 to 1. We have FA naught over RA as a function of a continuous variable x, giving us this black curve in here. And what I'm going to do is go out to my undetermined volume x1, keep marching out until the size of the box that I create by drawing a box from this point on the curve gives me the volume of that reactor V1. And then once I've found that point, I can march off another volume, this time V2, which takes me out to location x2. And these are the two conversions that I will achieve by running these two CSTRs in series. You can imagine that you could write a code to do this process pretty easily. And of course, that's probably the way we do it now. But it's a nice conceptual picture to understand that the volume of two CSTRs in series is typically going to be smaller than one CSTR that you would need to perform the equivalent job, as long as you're a 1 over rate curve concave up. Okay, let me go ahead and continue. We're going to do another example now. and think about generalizing this idea to a long series of CSTRs in a chain. So what eventually happens to this system? Well, if I have no conversion coming into the first reactor, and this time I'm going to make all the reactors have the same volume. Okay, so I'm going to make them also add up to one volume V. So I'm going to imagine taking a giant reactor volume and carving up into little chambers where each chamber pours into the chamber next to it. So each one now has a volume V over N, and they're in chambers. And I have a conversion X1 pouring out of reactor 1, X2 pouring out of reactor 2, on down, keeps on increasing until I get to Xn pouring out of the nth reactor. Okay, so we're going to set up equations just like the ones that we did above. We have 0 equals FA, FA naught minus FA naught times 1 minus X1, and there's the rate evaluated at conversion level X1 multiplied by V over N this time. Okay, we do that also for reactor 2, and all the way down until we get to reactor N. Here you have the flow rate of A coming into the nth reactor, flow rate of A leaving the nth reactor, and the rate of generation of A at the conditions of the nth reactor, all multiplied by V over N, because all of these things have that same volume. So now I'm going to rewrite these, and what I get is that the factor V over N each time, that is the size of the volume of my step down my Levenspiel plot, is going to be this constant volume step, and it's going to be equal to minus FA naught over RA, evaluated at the corresponding level of conversion and multiplied by the change in conversion achieved by that reactor. So this is the first reactor, and it achieved a change x1 minus x0. x0 here was just 0. We had no conversion at the beginning of this process. When I go down to the last reactor, I have FA naught over RA evaluated at the conditions of the nth reactor, and this is the change in conversion achieved by the nth reactor, going from xn minus 1 up to xn. Okay, so these are like little tiny Riemann sums, if you want to think of them that way. What we have done is basically done a construction where we're stepping off a constant volume each time. First one takes me to x1, second one takes me to x2, and we keep stepping up and up and up this curve. Of course, as the curve gets higher and higher, the rectangles get narrower and narrower, which means that each successive reactor is doing a little bit less in terms of conversion. But what's interesting about this is that if I take the number of slices in this diagram to go to infinity, then basically what we have is a plug-flow reactor of volume V. It is behaving exactly like a plug-flow reactor in that limit. Okay, so that's actually not so surprising. In hindsight, of course, the plug-flow reactor is like a bunch of little tiny volumes that pour into the next volume with no mixing across the two volumes. But every little plug is well mixed within. Okay, so that is a nice analogy, I think, that kind of gives you some intuition for how plug-flow reactors and CSTR reactors are related to each other. Comes across very clearly through these Levenspiel plots.